Hello and welcome to Func Prog Sweden, the final Func Prog Sweden for this year. And what a year it's been. We have seen presentations ranging from Clojure to F# to Scala, also into functional thinking, functional processes and everything. We've also seen new languages, EYG for example, and also Richard Feldman has been here and presented rock language. So we have, what a year it's been. So this is the final Func Prog Sweden for this year. So welcome everyone. So the agenda for today. First, right way. First, introduction by me, Magnus. Then building a type checker in Haskell by Christoffer. Like, ever wonder how type checkers work? Want to build your own? In this talk, you learn how to do it. A very simple type checker in Haskell. Then the final presentation for this year, Beyond Lambda Calculus, Relational Computations by Marcos. By combining logic and functional programming, a relational lambda calculus would come to offer a novel way to express the world. It's very interesting. I think it's nice that we end on that note this year. And of course, in the end, you want to ask more elaborate questions, join the post-show chat. First, I would like to thank also our video sponsor that's been with us throughout the year, Beat. Beat is an IT consultancy company focused on functional programming. If you want to know more about Beat, head over to social media or to otherbeat.com. Schedule then for the coming next year, 2025, 21st of January, we're back. We haven't set the date yet for February, and in March we'll be coming back to Kivra. So if you're in Stockholm, please check out the date. As soon as we have finalized the date, we will announce it on MeetUp and on social channels. So check out the date and make sure to come to Stockholm and Kivra in March. If you want to support Func Prog Sweden, which of course you want to do, head over to MeetUp and join the group or subscribe on the YouTube channel. Also, if you want to ask more elaborate questions or want to hang out with other people loving functional programming, join the Discord server. You can find the invite in both the MeetUp group and on YouTube. And if you have questions during the presentations, just fire them in the chat or ask them on Discord, and I will read the questions up to the presenters. With that, then let's start. And warm welcome, Christoffer, to Func Prog Sweden.
Thank you.
Yeah, warm welcome, and you will start the first presentation, writing a type checker in Haskell.
Yes.
Now comes the trickiest part of this presentation, is that I will give Christoffer the cable.
The handover.
The handover.
Let's see how this works.
Hopefully it works well.
Okay, there we go. Yeah, I can
Welcome.
see it. Hopefully the people on the stream can see it as well. Okay, so hello everyone. My name is Christoffer, and I'm going to talk to you today about writing a very simple type checker in Haskell. And don't worry if you haven't used Haskell before. I think the presentation is simple enough that you should be able to understand it either way. Yes. So who am I? Like I said, my name is Christoffer. I'm cracky.com on Blue Sky. So, if you want to get in touch with me, that's probably the easiest way. And I've been kind of interested in programming language theory recently. And so basically, I learned this stuff quite recently. So now I kind of want to share the things that I didn't know like a few months back, basically. I also run a company called Functional Software. And surprisingly enough, we work with functional programming. So, yeah, if you ever need like functional programmers to staff up, or if you need consultants, talk to us. And we have a website as well. I heard you're supposed to have that in this day and age. But like Magnus said, if you have any questions, don't be shy. Just ask them in the Discord or the YouTube chat, and I'll try to answer them as well as I can. Oh, yeah, I forgot to mention, our mission is to spread functional programming. So, I don't know, I think we can all help out with that. Okay, so today we're going to talk about type checking. And just to orient ourselves a little bit, like the type checking happens as part of the compilation of a program. And usually this happens after the parsing step. So what we will get as input to our type checker is the abstract syntax tree. Okay, so basically what is a type checker? So a type checker looks at the terms in the abstract syntax tree and determines what their type is. And if we find that the term is like well typed, that it type checks, we return the type of that term. And you can sort of think of it as a recursive function of terms to maybe types. And yeah, our type checker is going to be like super simple. This is not like production ready stuff. So a real type checker would probably return something a bit more complex, locations that tells you where the type error was, etc., etc. And the language we're going to be type checking is the type Lambda calculus. And we're going to keep it like really simple. The type Lambda calculus is basically just functions, but we will also add the following extensions: Boolean logic and integers, just to make it a little bit more interesting and to make it more obvious where the type checking can fail. And just to give you some like feel for what like this pretend language could look like, we have some example terms. So 5, for example, would be an integer. True would be a Boolean. Then we have an example of a conditional. And then a variable. We also have functions and function application. And if you're not like familiar with ML-style languages, that last one might look a bit weird. It might look like I put the parentheses on the wrong side. But that's because traditionally, function application is made in ML-style languages with a space. And yeah, when I say application, it's also referred to as like calling a function. Function application is the fancy name for that, I guess. Okay, so with that, we can start writing our type checker. So the first thing we need to do is to have some kind of way to represent terms. And we'll start simple. We'll just represent integer and Boolean literals. And to do that, we introduce a type called term. We also introduce a type. So now we kind of get into like meta territory here. But we start with just like defining types for integers and Booleans. And Booleans, or sorry, literals are basically the easiest term to check. Each literal will have the type of the literal, basically. So an integer literal will be a just int, a Boolean literal will be a just bool, etc. So the type checker just checks, like, okay, what kind of literal did we get, and returns the appropriate type. Okay, so now we can make it a little bit more interesting. Let's add conditionals. So conditionals are a bit more complex. A conditional has 3 terms. First, you've got the like condition term, and then you have 2 body terms. So we can represent this as a triple, like 3 terms, basically. And as you can see, we need to extend our term type to accommodate this. And just to, like, as an example, if we had this pseudocode, if true, then 1, else 0, like some code for turning a Boolean into binary, the syntax tree would kind of look like the AST you can see there below. So it's a conditional term with first a bool literal and then 2 int literals. Okay, so how do we check conditionals? So we start by recursively running the function or the check function on each subterm. So first we check the condition term, then the first body term, and then finally the last body term. So C, T1, and T2. And the typing rule for conditionals says that the first term must be a Boolean. And there's another rule as well that says that both body terms must have the same type. So, and then we know that if this is true, then the type of the conditional will be the same type as the body terms. So you can see there, like, if we successfully type check all the terms in the condition, then we will return the type of the first body term. And if we look at how this might look in the syntax tree representation, like it looks, well, first we have a bool literal, then an int literal, and then a second int literal. And this type checks because all of the typing rules check out. Like there was a bool literal, which evaluated to a bool type. That was the first term. And then both of the body terms had the same type. So this should return just int. And for example, if we try to put something else in the last term, then the type checker will fail because, well, the int literal and the bool literal, they have different types. So then we return nothing. Okay, so next we'll try to type check functions. And the function consists of a variable and a body. And if we apply the function with an argument, then the variable will be replaced by the argument in the body term. And we can also say that the function is a type that maps one type to another type. Okay, so what are the rules, or like how should we type check functions? And this is when it gets kind of complicated because previously we could just look at each term and determine, like just from looking at it, which type the term had. But this example here, like, okay, what should x be in this function? I mean, intuitively, we know that it should be a bool, but how do we actually mechanically check this? And one way you can do it is to just leave the term, or like leave the variable untyped, and then you go in and examine the body and see what kind of like type it looks like x has. And this is the idea behind the Hindley-Milner type inference that you might be familiar with from Haskell. But yeah, this is like just a short tutorial. It's not like a university course, so we'll keep it simple. And the simplest solution is just to require a type annotation in the function. So as part of the function term, we specify a type, which says that x has to be a bool in this case. And then we go ahead and type check the function body. And you can see that there's a sort of like switching here, that before we sort of type checked from the bottom up, like we recursively examined the terms to determine their types. But now we sort of go the other way around. So we sort of say that, well, x is a bool, and given that, we can type check the rest of the expression. So we sort of switch from going like top down to bottom up instead. Okay, so how do we type check functions? First of all, we need a new function type. And we also need to extend the term type so that we can add lambdas. Just like I said before, like lambda basically has, and lambda is just a fancy name for an anonymous function. And like I said before, there are 3 things in lambda. First, we have the input type, which is the first part of the triple. Then the function name, and that's just a string. And finally, the body term. And to make it a bit more like interesting, so we can actually write a complete function body, we also need a way to handle variables. And this doesn't introduce a new type, but we need to extend the term type with a representation for variables. And basically, the only thing we need for a variable is the variable's name. Yeah, represented as a string in this case. Okay, so a simple code example of how the abstract syntax tree might look for a parsed function. We have this same kind of thing. We take a bool and then we turn it into either a 1 or a 0. And then the AST might look something like the example below. And you can see that, basically we put the type first, which is bool, and then the name of the argument. And then you can see that the conditional kind of looks like it did before, but instead of a literal, we use the variable x. Do we have any questions so far? People are really, really attentive, maybe. Okay, so how do we check variables? And now we need to make the type checker, we need to extend it a little bit, because we need some way to remember which variables were introduced by Lambda. And in order to do that, we introduce something that's called a context. Basically, the context is a mapping from strings to types. And in case a variable is defined in the context, then it type checks. And if we don't find it in the context, we consider that a type error. Yeah, sorry, I forgot to mention that also the lookup function here will just give us the exact behavior that we want, because if the variable is missing from the context, it will return nothing. Okay, so how do we check lambdas? So first we need to first we add the argument to a new updated context. That's the first line there. We insert the argument into the context. And given this updated context, we can check the function body. And the return type of the lambda will be the type of the function body. So we can return a function type which has the input type as the first parameter, and then the type of the body will be the second one. And just to give a bit more concrete example, if you have a function like this, this will actually, this will type check successfully, because like you saw before, we take a boolean as an input, and then we reference the boolean variable in the first in the conditional. So this type checks, and it returns a function type of booleans to integers. Okay, so what's an example of a function that doesn't type check? So for example, if you say that the function takes an integer as input, and we try to use a variable in the first that variable in the first position of the conditional, it will fail because, it needs to be a bool. Can't be an int. So then we will return nothing because it doesn't type check. We're getting close to the end now. It's just one more thing. Function applications. So it would be quite boring not to be able, or to only be able to define functions. We also need to be able to apply them. And we start by adding a application type an application constructor to the term type. And the application has two terms. So the first one is something that's supposed to be a function, and the second one is the argument to the function. And as you might have guessed, the first thing we need to do is to check that the first term is actually a function. So we run the checking function on the first term and verify that it is actually a function. If not, we return nothing. And then the second thing we need to check is that the argument type has the same type as the function's input type. So we need to check the type of the argument and make sure that it matches the input type of the function. And if that checks successfully, we can return the function's output type as the type of the entire expression. Otherwise, we return nothing for either of those cases. So let's say we have a function like this. It's just the identity function for integers. And the syntax tree might look something like this. We take an argument, we take a int literal and a lambda as arguments to the application. And this will type check because we supplied an int literal as the argument, and the type of the int literal is int, which matches the input type of the function. And then we return int as the type of the expression. So what happens if we try to use it with the Boolean literal? Well, that will fail because, well, true is a bool literal, and that does not match the input type of the function. And yeah, that's basically the whole thing. So now you can type check the type lambda calculus with booleans and integers. You can make your own little programming language. And it's actually like the type lambda calculus is actually quite powerful. And another interesting property that it has is that it's total. As in, if you have a program in the type checks, you can be sure that it actually completes and it doesn't crash. It's not Turing complete, however, because you don't have any. We haven't added any recursion, and yeah, there's a lot of other things you can extend it with. But yeah, if you have any questions, don't be afraid to ask them on the Discord or on the YouTube comments. And like I said before, I'm at trekkie.com on Blue Sky, and also you can check out functionsoftware.se. Oh yeah, I also have some like reading material, if you like this. First of all, this presentation was heavily inspired by a paper called Bidirectional Typing Rules, a tutorial by David Christiansen. So you can check that out if you want to learn a little bit more about this and some more advanced type checking topics as well. Also, the book Crafting Interpreters by Bob Nyström is really good if you want an introduction to like the rest of the compiler pipeline. So if you remember that one of the first slides, that will take you through the parsing and the lexing, etc., of a programming language. Also, if you want to like get into the world of type checking, it's quite useful to be able to read the notation used in papers. And there's a very good post on langdev.stackexchange.com, which is called "How Should I Read Type System Notation?" I can put all of these links, well, somewhere in the comments on meetup.com, maybe. There's also like a really nice free course online called Data Structures and Functional Programming from Cornell University, which has a chapter on implementing a like ML-style type checker. Yeah, that's it for me.
Thank you very much.
Should I pull this out or?
It doesn't matter. You do as you like. Thank you very much. Actually, I have 3 questions from the chat, from the viewers. First one, do you know any full but similar, simple and similarity styled implementation of a type system with all of the primitives?
yeah, that's a very good question. Short answer is no. But there is a paper that I've heard a lot of good things about, which is called Implementing Haskell in Haskell. And people have said that, like, if you want something that's a little bit more realistic, because I mean, really, this is like a pretty basic toy example. I think that's a good paper to check out. There's also a book called Types and Programming Languages. It's a bit dense because it's a course, it's a university textbook. But if you like walk or if you work through all of those examples, you will end up with a working type checker for like something that looks a bit like standard ML. And also the Cornell course I mentioned that in the last slide also pretty much does the same thing. It's a bit simpler and a bit less theoretical, I think. So that could also be a good place to start. Okay, more questions.
Yes, favorite functional language.
Wow.
Then so far. Do you dare to answer that?
I don't know. Like, I haven't been programming that much in functional programming languages in anger for very long. Like, but I'm actually, I really like typed functional programming languages. And I mean, Haskell is really cool. I was going to try out OCaml for this year's Advent of Code. Then I remembered that I don't have any time.
Time.
So yeah, and apparently that's like a requirement.
Yeah, time is a requirement.
Yeah. But yeah, I really want to try out OCaml. I'm heard a lot of good things, and it looks interesting.
Next one, which is not a question. It's like, can you share the reading materials on Discord later? Well,
yes,
Christoffer can do that, so he will share it.
I will share it on Discord, and I can put it in the MeetUp comments.
Thank you very much. Also, Peter in the chat said there are some good F# examples. Let me find the repo. So, Peter, please post them here, or just post them in Discord or on below in the MeetUp chat, and people can find it. Or in the MeetUp, I think it's comments, maybe not the chat. Yeah, again, thank you very much, Christoffer. Thank you for coming to Func Prog Sweden.
Thank you for having me.
Also with the short notice. Thank you very much. Thank you. And now we'll head over to our second presentation for today, Beyond Lambda Calculus. Relational Computation by Marcos. And I'm not going to try to pronounce your last name because it's going to not go right. So I'm sticking with Marcos.
Right.
Welcome
okay.
to Func Prog Sweden. Yeah.
So, well, it's a pleasure. I'm really glad to be here.
Yeah, you're welcome. Hit it away.
All right. Let me just see if my screen will be there. I think I'm sharing already. All right. So today I have a very bold title. I hope I can present a topic that's very dear to my heart. It's at its core something that introduced me to functional programming back in the day. Funny enough, well, we can talk about that, but yeah. So the topic of the talk is Beyond Lambda Calculus, Relational Computations. So my plan here is to invoke, so to inspire a new generation, if I can be such a dreamer, of new languages that try to aim at the target of relational computations, but using some of the features from functional programming. And I'm going to share a few of them, a few examples, and give more of the path that I had all of this time. So a little bit about me. So this talk, I wish it was about Emacs. I could just talk about Emacs all day. So yeah, I'm an Emacs user, that has to be said. I do functional programming for a living. In fact, I've done it for all my career up until this point. I'm very glad of that. But I'd also like very much relational theory, and that goes hand in hand with database theory. So I've been very eager to research more on the topic because of its foundational history. I do F#, so I do .NET. If I have to, if you point a gun in my head, I can also do C#, but it's not really what I like. I prefer F#. I also like Common Lisp, and I'm not good at it. People say it's the Java of Lisps. I tend to agree, but I think it's fun. I like classic menswear. That's something about me, and I'm very interested in semiotics. And I call myself an amateur proto-logician because I'm still studying. But if you want to hit me up, I think the best places to send a message, a direct message, would be LinkedIn. But you can also follow me on GitHub, and there's my email, my contacts all in there. So what are the goals for this talk? I want to present first the problem that I had to confront back in the day when I started researching on the topic. I want to inspire. I want to bring about a new way, a new outlook to our relational world, how we can perceive the world with relations, and how that can help us to make more conforming programs, computer programs, with the things that are present already in reality. And present a what-if scenario. What if we had a computer doing this process for us? All right, so let's start with this quote here, which is, it's basically stating that in a declarative world, you are more concerned with abstract specifications rather than its concrete implementation. So that is analogous to say that when we are looking at, for example, an implementation of a binary tree, or I'll pick SQL, I think it's better. If you are trying to implement a table, like a relation in Postgres, let's say, you are more concerned about how it is normalized, how the table looks, and how it represents structures, instead of being concerned of how it's organized in the disk. If there is something like a zookeeper underneath and distributed, the tables distributed across the disk, that shouldn't matter for the specification of that entity. And then you can stretch that over to programming languages and how they express state, for example. So there's this chart here from the famous book of Peter Van Broy, and I think it's a very nice chart because it puts things in a spectrum. You can't really just say that something is declarative or not. So I think it's more of a spectrum that we can observe with the interactions in the state. So in one side, we have, for example, less declarative languages and then more declarative languages with its usage. Because no language is just pure that thing, so it makes sense to isolate them by their features. So if you look here, for example, you can do OCaml. Why is it paired with Java? Because you can do stateful functional programming with OCaml at the same time that you can do just functional programming with OCaml, but also imperative programming with OCaml. So it's a language that it's spread over this chart. And then on the other side, you have languages like Prolog and some SQL embeddings that allow you to do relational and logic programming. But you can also do, on the other side, software transactional memory that is very expressive in the state. So this is the importance of the state and how it plays into you, so you can define the program. I think it's a very nice chart. All right, so this is a definition of a program that I have for a project I've been working on. And I was trying to do a relational engine in OCaml. So it's a Perl database that basically I can do relational algebra inside of it and search things in the disk and present them, retrieve data and store data and so on. And then this is basically Nix. So this is my Nix flake. And if you look here, I'm basically defining my package that is built using this function called a build Doom package that basically specifies how the program is built using DOM, giving my inputs, environment variables, where the source code is presented, some custom commands, So it's a very nice way to remove the burden of the build system, in this case, to be system agnostic. If any Linux distribution, so long as it has NICs, it can build this OCaml package. If depending on the architecture, I can build to different architectures, and that abstracts it all. In this case, I'm even building on macOS. So one example. All right, so some people asked me when I dropped the summary for this presentation about what would be the philosophical listing for me to claim that we are ontologically committed to relations. And these are three of the important people that I think mark a philosophical concept that is very important to me. So classical philosophy, semiotics, and modern logic, more of an analytical tradition. So if you look at Aristotle all the way to Frege, through this is John St. Thomas or John Poinsot, with that started the modern semiotics and later got picked up by Peirce. You can see that the relations are the core presentation of the Aristotle's predication, but it's also the contextual analysis of the sign in semiotics, and they are everything basically in second order logic. So I think this is a very nice picture. I will not get too much into this, but I would appreciate to have a conversation on this if somebody wants to reach out. I think there is much to be said here still. All right, so let's start with some examples, and so we can see how people are using this. So I was researching not long ago about how concurrency diverges from parallelism. It's often not very well explained, and many people have different definitions. And then I came up across this definition from the Sun Microsystems manual back in the 90s, that it basically says that the parallelism is a condition where threads, they're executing simultaneously in time, and concurrency is where they are executing, that is making progress, but the notion of time can be shared. So they are not necessarily executing simultaneously, but time slicing the time for the processor so they can execute. So that would be the representation of concurrency. And now if you think about it, then the only categorical difference that exists between parallelism and concurrency is derived from the interaction of the threads with the state, which is with the time, which is the shared resource in this case. So you could even say that the concurrency in this case is just a relation of is just the representation of the relation in the relationships of the threads with the time. So that's food for the thought. This is an example in OS. I think it's a very cleverly designed language. I think it's a shame that it's not very well known. I used to not know it very well, but I was just checking it, and it's amazing. It has so many good features, and it's multi-paradigm. So it has many different constructs inside of it to allow multiple paradigms. And it has logic implementations inside of it, but also procedural and functional inside of it. So here we have, for example, just translating this code because the syntax might seem a little arcane. We have a thread that is synchronizing, unifying, that it needs to unify this n variable. And then this n variable is the condition for this OR. So this is a disjunction in here. So this is basically the commas in Prolog or Erlang. In Erlang, they have just syntactic meaning, but in here they actually fulfill the goal of branching out the structure of a logic search, right? So what this program will essentially do is simulate give the foundation for a producer and consumer design. So this thread will only start to kick off when you can unify the number n, which is down here, and this thread will only kick off the s, which is needed after this thread is completed. So it's a way to bind things and make things synchronized through relationships of the variables that are shared in this scope. Okay, how are we putting relations to use them nowadays? So this is more of a review of the things that I've seen people doing and how they are doing it. So there's this paper from 2006 that I think it's formidable. It does a very good research on presenting what drives complexity in most of our programs. It's a very famous paper called Out of the Tar Pit. I got cited multiple times already in various conferences. But it presents flavors of complexity. So it presents, for example, this case here, there's more to be said on that, but just for our context, it's suffice to say that it talks about state and control. We are in a functional programming conference. I think most people would realize that, yeah, state is indeed a hassle. We do all of these strategies to hide the mutation of state. Mutation of state makes it very hard to reason about programs, about the logic of things. Control is a little bit weird, though. It's not something that we often think about it because control is more of about the structures that lead that tell the program how to run, right? So how we're supposed to compute something. And then it presents what we want to keep of each paradigm. So it presents logic programming, OO, object-oriented, imperative programming as a flavor of it. And it also presents functional programming as the mainstream alternatives, and then it tries to pick what is meant to be kept of each paradigm. And then it proposes a specialized languages for each scope instead of proposing a general language. So when we are about to start a project, we have a plethora of languages. So we've got here my beloved Emacs Lisp. You've got Java, you've got Microsoft Java, you've got some Erlang, you've got many options to choose, and some of them, they somewhat try to blend the usage of the database, for example, that is supposed to represent this relational outlook to data with the code. So for example, in .NET, you have Entity Framework. But what ends up happening is that Entity Framework, for example, alienates the relational aspect from the main language through ORM, basically. So you're dealing with the internal structures of the language instead of the relational part that is supposed to tame state. So, and it's not the same. It's not the only language that does this. Many others, they fall in this category, but some present different outlooks on that. All right, so this is a closure example, and Rich Hickey, on his talk on Datomic, he presents the very idea of bringing the database, trying to not alienate the database and bringing it closer to code, so to the logic of the program. So in Clojure and Lisps in general, there is the concept of homoiconicity. So it's much easier for you to bridge the gaps with some syntax that is commonly shared between both. So in here, some Clojure might look, Lisp in general might look a little weird for most people. So I'll just present more or less what it's been done here. So there's these transactions that we are executing to insert these entities on our database, on Datomic. And then this is a query that we do with relational constructs where we bind the same entity that produces these attributes that we are trying to search. And then it just displays all of them. So it tries to go on the database and unify the tag, the email, and the name that we have inserted. So it should present those in a list. And then here I have a function handler that was basically, there's some other machinery behind of it that is listening to the atomic transactions. And as soon as we insert one of these, it will go through this search the structure and present it on the screen what we have just inserted with the timestamp. So this is basically to show that we can bring the database closer, so the relational part closer to the code, to the logic of our code base, instead of just having it SQL strings somewhere else. Okay, so there's this other paper that presents something that started to open my mind, which is it claims that algorithms are basically logic and control. So the logic part would be basically what is to be done, and the control is how it is to be done. So often when we are coding something like a Fibonacci or factorial algorithm, it's very clear that we are trying to bridge the control components is very it's the core concept of the algorithm. So it's right in the middle, and that's the thing that defines the state management of it. So this separation is attempted, at least to a certain extent, to be done in relational databases like Postgres, SQL Server, Oracle, and so on, but it's not really on programming languages. There is this very thin, we don't try really to diverge the logic from the code, from its control. That's a very weird concept that we haven't explored all that much. Okay, so just to give an example, so this is a expression that they do in horn clauses for defining relations by recursion. So in this case, we have a contains. So this set is containing here. If it's empty, it's already true. It holds this predicate. This relation holds. If it's not empty, then otherwise you need to split and then apply recursion to construct the subsequent until you get the elements that are contained in it. If all of them hold, then that's true. Okay. But I think Cod knew better. If you look at the papers from E.F. Cod back in the 70s still, he talks about embedding a sublanguage. He was working on a language called Alpha that would be a candidate for embedding into other programming languages that would allow us to do second-order logic, predicate calculus with second-order logic to retrieve data. He later retracted that idea because he saw that it would in the end make data undeterministic. So decisions would be undecidable. You would have relations on top of other relations, and that would make it harder. So we take for granted notions such as, for example, if I say King Canute is one of my ancestors, that sounds easy, like a normal customary assertion, but there's much more to it. You can't express that assertion in first order logic because you're now quantifying a set of people and trying to define the relation on the set. So you need to find now a set of people that is ordered with ancestry, the relation being ancestry, where you can order you and King Canute in time, and then you can prove that you are indeed that you can hold the predicate that you are an ancestor of King Canute. In a database, you would encode this with first order logic by doing a closed world assumption where you basically specify that this is just true. So there is this and there is this guy. They're both related. They are an ancestor of one another. So it's one way to circumvent this problem. So we can still do it, but it's not nearly as powerful as it would be with second order logic. Okay, so what's the vision then? What if we had a language that could bridge the gaps between the data handling and the logic? So to manipulate the control and the logic, that they are distinct, they are on their own parts, yet they are a cohesive part of a language. So if there's something like that, that's the first question. We would also need a language that is capable of describing relations as part of our business domain, of our business modeling. That would be very helpful. Again, with that idea of alienating the database. We would pull the database to the code. Constraints. We would basically, how we would constrain our data with, be it with equations. There are many strategies, but we do it with types, many other schemas, and so on. So how would we constrain our data? And is there a possibility of abstracting the state? We don't want to deal with the notions of state all the time. That's a no-brainer. And the last is possibly express modularity. So I'm not going to talk about this. I'm going to go on. I'll present this on the demo if we have the time. So let's make a quick review of how current logic programming is. So this is basically an AST. This is a very simple and very minimalistic AST. It's basically using de Bruijn indices. I'm not sure if it's Bruijn. I'm not sure about the pronunciation. But it's basically using integers to mark the notion of the variable. So we have it defined as a meta variable, so a variable that we can unify and we can find elements. And we have predicates. So predicates, they would be just, they're also another name for them is functors, which are essentially, if they have an arity and they have other terms inside of them to dictate, to say if a value is true or false, if it holds. So a predicate with arity 0 has an empty list, and that's just a fact. So that's an atom, for example, in Erlang and Prolog. If it has 1, then it can have one gap inside of it, and then that's a predicate that depends on that value to be held. If it is, for example, an atom that is inside of it, then it's just a fact. So I could make a quick example here, but I'm just going to keep going and present them at the end. Okay, so unification. So when we're talking about unification, we're talking about syntactic identity. So we're trying to identify how two things are equal by a series of substitutions of infinite procedures that we can reduce the variables to terms. So we can equalize both. So one example of that, and we heard of that on the last talk, was from the Damas-Hindley-Milner type system. It does unification on types. The types are essentially whole, like generic types, let's say. They're essentially holes in the domain that you need to unify to find the possible constraints that you can enforce on that type. So unification is very important for this. So backtracking, it's a very interesting concept that is cooked in some languages like Prolog, that it allows you to explore the difference between the branches in control flow. So if you have like an if, for example, and a variable that's being unified in the if, the variable might hold or not, and then you will need to explore the possibilities of the branch going on the then clause and on the else clause. So you will have to test the cases and go back on this bifurcation. So you are here, and then you go here, and then you explore, and then you discover that you fail, so you backtrack, try the alternative, and go on. Another one is determinism. So we introduced non-determinism by basically exploring those choices, right? So when we are looking at a branch, and we look at let me go back here. When we're looking at a branch, we might go back, and then we have to undo side effects that we might have caused on this. So we would have to go back, and then we explore another alternative. The operator here we are talking about is choice. Choice is the definition of a non-deterministic algorithm. So we're exploring a list of values that are possible solutions for this concept. So if there's only one, then it is deterministic. If there's multiple choices, there's multiple outputs for it, then it is non-deterministic. Okay, manipulating lists often it results into non-determinism with constructs. If anybody is interested in implementing something that is just logic programming, there's this paper. It's actually a book, more or less, that just gives you an instruction set, and it explains very nicely what we can do about it. In fact, we're doing that now. Me and a group of friends, we're implementing a language called Karuta that tries to implement this with bindings for manipulating data and first-order logic as well. Okay, so now what if we change the approach? What if we mix both? So what if we pick the good things of functional programming and the good things of logic programming, and we merged both. So that's a question that's been on the debate for quite a long time already, but just now it has started to pick up momentum. So one of the core things that we would have is higher order pattern unification. So I did some sort of this AST here. So you can see that it grew substantially with the Lambda calculus constructs. So we have now a free variable, a meta variable that we already had, a local variable, and they're all with integers. So we don't need to have the parameter here in the argument for a Lambda. And we have essentially a term for the Lambda, applications of things that we can reduce to Lambdas, and terms that we can apply to those Lambdas. And in the end, the predicates just like we had before. Now, if we are to unify this, it's easy to see that we now have Lambdas. How do you equalize two functions? How do you unify and make the two functions equivalent? Well, you need to do beta reduction. So now it's another problem because you now are trying to beta reduce functions before you start unifying. That we have algorithms to do something of the kind. We have this Gerard Way algorithm, and it's semi-deterministic. So it's good. It's very efficient, and it's very simple at its core. It just produces more branches and more data so it can test. So in the end, it can just prune the data it doesn't use, but it's still semi-deterministic. We do, however, have decidable parts inside of our program that we can unify. So, for example, variables with integers, we can unify them to the integer that we want. So we can unify those first. And in fact, that's what the linear algorithm, that I forgot the name now, but there's a linear algorithm that does that, and it's used inside of Isabelle and Lambda Prolog to do it. Okay, so what's the gain of this? What do we gain by doing all of this? It seems a lot of trouble. There's this nice property with functions, which is we can analyze their injection. So if we have one set and we have another set, and each value of one set maps to the codomain, maps to at least one element of the codomain and to different values, then it is we call it a one-to-one function. It's an injection. If it's a surjection, means that there are some values on here that map to the same value. So one function that we could say, for example, that is like x squared. You give -2 and 2, and it produces the same value. A bijection would be that they map exactly to 1 because they are 1-to-1 and on 2. So each element of this domain is mapped to this. So in theory, this is the necessary component so you can invert a function. If you can invert a function, think of the possibilities that you can do with it. Look at this example here. We have a pretty print function that can receive an AST. How is it implemented? It's unified with a source that we don't know. We want to discover the source code that produced that AST. So we unify the parse function that we already have implemented with the meta variable source with the AST. It produces us a unification of it, and then we can now print the source because we know a way to print strings. So this is a very nice use case and to showcase how powerful the idea of manipulating this the relationships between the functions as relations yield us. So there's this paper that I read, and it's absolutely beautiful, that they describe a way to implement a language that is a relational calculus. So they themselves implemented their own. So they go deeply into proofs, and they make usage of it's the best usage I've seen of Church-Wasser for trying to identify equations that, for example, produce the same values. They discuss their technical challenges, and they present an organized introduction that is very easy to grasp if you don't know really much of the theory yet. Okay, so now let's try to take a look into some examples. So I've got some here, and of course, and inside of Emacs. So let me do that. So first of all, we have this web scraping example in Prolog. Let me just increase it a little bit. There we go. So this is from a blog of a guy that I really admire. His name is Benjamin Johnston, and he wanted to prove the power of Prolog. And he basically did a example where you had an HTML page, and you had a table in it showing the cities and their temperature in a weather forecast scenario. And then he defined this relation where you basically pick, I think it is easier. So this element is because of a library we're going to use. So it will break down the HTML elements and then try to observe in the children and look at the relations between the city and the weather and the temperature. In the end, we just grab the page, which is here. We grab it in a data string. We feed it to this load structure function from that library that basically loads HTML. And then we just feed the page structure to trying to find the city forecast. Results, these are all we find. So it's a very elegant way to do web scraping that is treating the web page, the HTML structure, as a database that we can query data from there, looking at the relationships in the case of positioning of the things in the HTML structure. All right, so another one. This is in Mercury. This is the Conway's implementation of the dining philosophers using one semaphore. So I'll show more of Mercury, but this is just to warm up. So we define a predicate where we receive a IO. So Mercury is a typed language, and it tries to do it tries to have some purity discipline. So in Haskell, you would have something like a monad IO, where you would handle the entire context with IO whenever you have IO in your code. And then you would have to propagate the IO usage to the other functions that are on the other side. This symbol here, like exclamation IO, it's basically a sugar syntax for these two. So it's basically destructive input and unique output. So we're basically defining these two in a single variable. I think it's easier to grasp. And then we define a semaphore, we lock, then we emit a signal. We define the philosophers, so Plato, Aristotle, Descartes, and Russell and Sartre, and they're all sharing the lock, and they're all sharing the IO, but this IO goes changing its structure. So for example, this function mutates IO, let's say. So it will produce an IO instead of IO0 that would come from this, it would be IO1. And then IO2, IO3, IO4, because there are different productions of IO from the input and output. So you would always have this interleaving of the IO following up. So this is our entire program. It's very easy to read and very nice to reason about it. You can basically see that they're all sharing the lock and they're all spawning philosophers. Now, if you look here, the other predicates that we have here, the philosopher, is basically being used here with as inputs. So we're giving inputs of the semaphore, the philosopher, and IO. And we are, you can ignore this. This is the Mercury. You have to type the determinism that is expected out of the predicate. I can get more into that in the other example. So we're passing down the who is the philosopher, the lock, and the IO, and then we get the name of the philosopher. We present it to the screen, so we cause the side effect on the IO, an effect on the IO. And then we wait on the lock, get the fork, and then we see if we have acquired the other fork. If so, we proceed into this branch where we set the global fork. So this is another relation that we have, another predicate that we have down there. We emit the signal, blah, blah, blah. I'll not get too much into this, but the point is, it's very easy to look and read the code that otherwise would be somewhat complicated to reason about the state change in a very simple, readable way. So you're clearly seeing what's going on here by just taking a look at the shared components that are being used. So in the end, we just do our configuration. We express the modes that we take care of. And then we just have the names. That's very simple. So this was just an introduction to Mercury. Now, let me show something that is perhaps more interesting. So I have on here a couple of examples. So there's this example that Wilbur likes to use with quines. So this is for mini Theorem. So Wilbur has many nice talks, and he's a very clever guy and very nice to see. So I'm going to use chess scheme to produce a program that can produce other programs for me. And I think this is the demo, not helping. Let me try again. Geyser scheme, well, chess. I am on the same folder. I think the path is not right because schemes imports, they are basically relying on the local path where I spawned the repo, and since I started Emacs in the upper directory, I will not be able to import it here. So I'll just explain what it does. You can check the 99 ways to say I love you. It's a program that it's more or less like this. You would put 99 here, and then this will try to unify the variable q with some interpreter, and this is something that you have to do on your end. So eval expression with this o, so eval expo, and then you have the q variable that you want to unify. So that would represent one of the variables that you are searching with a random context that's empty in this case, with this result. So if the program evaluates its logically equivalent to this, which is a list with hello Func Prog Sweden, then it would produce programs, in fact 99 programs that can evaluate to this. It's a shame I can show this because it's a very nice use case of it, but let's move on. So let's get into, I was talking about Prolog, so I have that backtracking. So this is Prolog. Just activate. So this is Prolog. Prolog is very interesting because we're defining these edges, and they're just simply facts. This is what I said about A having 0 arity, the same way the B, C, and the rest do. And edge has 2 of arity. So I could make a search, let's say, edge with A to B, and then I would basically be asking, hey Prolog, give me the nodes that have an edge to B. So it would be A, it would be just A in this case. If it was C, then it would have B, and then again just B. If you had E, it would have D, and so on. So you would have the alternatives in that. And then you can make a predicate that you can evaluate the path. So you could say, this holds if you have an X and Y where you want to get a list where the head of the list is unified with the first element of the edge with an intermediary element Z, and then this intermediate element you can recur using recursion with the Y that we want to search. So we are targeting Y, constructing the path along the way with this intermediary value. Okay, now let's just do some Mercury, and I hope I'm not running out of time. All right, so I have this code here, so let me just activate Mercury mode. So Mercury is a very nice language. So we can declare our module, then we implement. Unfortunately, the module needs to be the same name of the file. And then you would have the modules that we want to import. In this case, I'm just importing IO, int, list, and strings. And I'm getting defining my predicate, that is the entry point, which is the main, that is deterministic. And then the implementation is essentially just print hello Func Prog Sweden with a new line. So let's try to run that. sh. Okay, so I should have Mercury. This is the compiler. So we can compile Mercury to C#, Java, the Bean, Erlang. I'm not sure if it compiles to the Bean bytecode or Erlang. We can compile to C#, C as well, and assembly. So it's a very versatile language to interrupt. It's very powerful. So let's use high order M. Compiled. There we go. Got some warnings because I'm not using the imports, but that's fine. So higher order. There we go. Hello from Prague, Sweden. Easy peasy. Now, let's define a predicate that does something more with it. So I already said about the functions that being invertible, right? So we can be able to find stuff. So let's define a predicate, pred, we're going to have an addition. So we're going to add things. It's going to be deterministic. So we always have an output that is single. That's actually a lie because you could do something but let's focus on that to make it easier. So we're going to receive an integer where we're going to get the first integer as an input. We're going to get the second integer as input as well. And the third integer will be our output. So there's no distinction in a predicate of the things that you give. There is a distinction on the things that you give as input and output, but you don't get a return out of this. You're not like a function call. Although Mercury also has functions. I'll show them in a bit. So I'll remove this. And now here we're going to do define the predicate here, which I forgot. So we're going to add. We're going to get A, B, and C. And the definition, the implementation of this is essentially that C is equals to A minus B. That's it. So that's our predicate. It's defining a relationship between the C and the A and B with add. So, all right. So how do we call that? We can do add with A, with 5, and then put an X, which is our result. We're going to put a comma. So it's do this and this. And then instead of doing this, we're going to write an int. So to write an int, it's very simple. It's just going to do this. And in the end, we can also do io.newline where we pass the io. So this should find the value here, which is 10. So let's just run it. There we go, 10. Now, what if we change our predicate and we put out here, and then we put in here? So we're just changing the positions we're looking for in this definition here. So now, if we put 5 and put X here, what other number added up with 5 gives you 5? Well, 0. So let's see. There we go, found 0. What if I change to, let's say, 10? 5. So you can play around with this. You can define many different approaches. But this is just to show that you can manipulate whatever you want in here if you have different modes prescribing the input and output in Mercury. So you could do that. Okay. Now, just to end with this, I think this is the part that most people wanted to see, which is how to do high order functions inside of a language like Mercury. You have support of that. So let's remove this here. Let's remove that. So let's define a way that we can iterate over a list. And then I have this code here. So I'm going to just copy it because it's too much so I can type. There we go. There we go. All right. So this is a code I did off camera with where we're trying to find matching function. It's silly. It's just a demonstration. So we have candidate functions where they do different calculations. So one adds the y with 1, blah, blah, blah. This is a type of a function, by the way, but this is also a value. So if you look here, we can define function types like this. So this is a function type. It's a function that takes an integer. Notice the lack of mode here because it's just a function, it's not a predicate, with that outputs an integer, and you have an input. This is an in this list because that's part of this predicate. So you're taking lists of functions that go from int to int. It's deterministic, so this find matching functions will essentially run a list filter that is semi-deterministic with predicates that are semi-deterministic, and it will try to evaluate this equation that yields 10. So if the equation yields 10 with the inputs that it can unify, then it will yield that as a valid function on this candidate functions. These are candidates, and this is the equation that we're searching for. So we're searching for this higher order equation. We put 5 because that's the value we want the functions to be solved for. And then we call that to call the functions. And then we say, this is our matching functions we're getting as an output. We do an if it's empty, we just print there are none. Otherwise, we fold and show which one of them that indeed they match with this. In Mercury, this is a way to format structures so you can show. So let's just run that, and let me bring that again. So I'll just compile. Nothing exploded. There we go. So it found 1, and indeed there's just 1. There's just 1 here. So it's this 10 minus 5 yields 5. So if we put 5 here, another function, so it found 2 now. So the fact is you have now a list of them that you composed, and now you have access to the function that you refined through some process like that. If I wanted, I could remove this, for example, and try to unify for values in a constraint. So that's something that some languages do, which is narrowing. I think Curry, which is another functional logic language, does. You can narrow by equations and constraints to reach a state that you want to deal with. Okay, so that's it. I think I went through a lot already. So we can end here, I think. So questions?
Thank you very much, Marcos. Thank you very much. So far, no questions in the chat. I'll shoot one immediately. Mercury, do you know if it's used in any production environment or any like, is anyone using it for real, or is it just used in university for research?
There is, in fact. There is a I don't know if they still use it, but I know that Prince, the PDF formatting tool, it uses Mercury to basically do the relationships of the layouts. Because when you have a web page with HTML and CSS, it's not very easy for you to do page break, right? So they use Mercury to define that kind of stuff. And it works very well. I heard things about the government of Hungary using that as well, but that seems to be a use case of some department of the government doing research with medicine, basically. So it's Department of Health, something like that.
Yeah. One more question: is Mercury the one, or is like? I'll rephrase the question. Which language you feel is closer to the dream in your experience? Is Mercury the one, or is there anyone closer?
Sorry, can you repeat which language?
Which language you feel is closer to the dream in your experience?
Right. I think in my dream, Mercury is very close to that. But I don't think it expresses some of the things that I like. I come from SML, F#, OCaml. So modularity there is king. I mean, maybe not in F#, but certainly it is in OCaml and SML. And Mercury doesn't implement that all that well, I think. I might be misjudging the language, but that's my perception of it. So I think OS is somewhat more interesting at that. But yeah, I think these languages tend to be more on that side of the modularity, right? But I think they're good. I would totally use Mercury to do my personal stuff. And as I said, it compiles to other languages, right? Yeah. So it's a very nice approach.
It is. I never heard of it before. I quickly Googled while you talked about it and found the wiki page and just scrolled through it quickly. Yeah. Thank you for sharing Mercury and also OS. I mean, we haven't had that on here, so thank you very much, Marcus. Let me see. I don't have any more questions in the chat. So again, thank you very much, Marcus, and thanks for participating and sharing in Func Prog Sweden. Thank you very much.
Okay, I appreciate. Thank you very much.
You're welcome. And now we're like on the final note for this year. We'll be back next year with more Func Prog Sweden and more sharing and more good presentations and more fun stuff. And until have a nice Christmas and a happy New Year, and then we'll see you next year. Bye for now.